Hi coders, how's it going? My name is JC, and today we're talking about instancing. Instancing is used to draw multiple instances of a mesh with a single draw call. It's an efficient way to minimize overhead. It helps to optimize the number of draw calls we need to record into the command buffer. It also helps to reduce the memory footprint of a scene. We will look at 3 different applications for instancing. Number 1, instancing based on individual game objects for each instance with support from the JSON scene loader and integrated into the scene graph. It can be used to create environments from building blocks. The second instancing application is shader based. It has a single base transform. For each instance, a local transform is derived from a height map. This implementation can, for example, be used for a grass shader. The third application for instancing is a particle system. The particle system uses a single game object per particle. However, particles are not integrated into the scene graph. This is for performance reasons. Parenting particles to a group node means an extra mat4 multiplication per particle, which can get expensive, especially for larger pool sizes. We will look at the performance improvements Vulkan Instancing provides. We will compare a cube made up of 2048 candle instances to 2 non-instance scenarios. One with individual draw calls and one with all candles merged into a single big mesh. But first, welcome to my channel. We're doing a mini-series about game engine basics at the moment. We encountered instancing in previous episodes. In the first episode of this mini-series, we saw how instances were defined in JSON scene description files. We talked about the scene graph and our tree walker function update transform cache. This recursive function traverses the scene graph hierarchy to compute a global transform for a node from its local and its parent global transform. The new feature now is that the global transform is no longer stored in the transform component directly, but in an instance buffer. The instance buffer can track if a re-upload to the GPU is required. In the second episode of this mini-series, we looked at 3D file loading. The loader creates the instance buffer in the function createGameObject. The loader can also be used to specify if instances should be supported by the scene graph. We will today go back to the 3D file loader and take a look at instance creation. In the third episode of this mini-series, we looked at a material and resource system. It provides the descriptor for the instance buffer. Be sure to watch those videos as well. So, on the Vulkan side of things, instancing is almost trivial. You can state the number of instances in the draw call, then in the vertex shader, use the built-in variable GLInstanceIndex to retrieve per instance data from an array, and Bob's your uncle. For the draw call, I use vk command drawIndexed, since my game engine always provides an index buffer. vk command drawIndexed takes the number of instances as an argument. Here in the vertex shader, you can see that I use a storage buffer for the instance array. You could use a uniform buffer, but be advised, a uniform buffer is limited to 64 kilobytes. I'm using a mat4 for the transform and a second mat4 for the normal matrix per instance, which have a combined size of 128 bytes. The maximum number of instances with a uniform buffer would be 512 instances. So you might as well use a storage buffer from the get-go. Now let's take a look at the following 3 applications for instancing: scene graph-based instancing, shader-based instancing, and a particle system. Our first use case, scene graph-based instancing, can be used to create scene environments. Here in the JSON description file, for each model, a top-level transform is specified per instance. Here we pass the number of instances to the 3D file loader. The loader loops over the node hierarchy of the 3D model for all instances. In the function createGameObject and only during the first iteration the loader creates the instance buffer and adds an instance tag to instance 0. So the game object for instance 0 can be used to get a hold of the instance buffer. The instance tag also contains a list of the game objects of all instances. The list of game objects can be used on the application side to retrieve the transform for each instance individually. Let's take a look at the instance buffer. The buffer data for the instance transforms resides as 2 copies both on the CPU and GPU. The instance buffer class manages those 2 buffers. It's a wrapper for a buffer on the CPU side that, whenever written to, sets a dirty flag. The instance buffer class is also a wrapper for the corresponding GPU storage buffer. Before the draw call, we need to call update on the instance buffer. This will flush the CPU buffer to the GPU if any element was touched and reset the dirty flag. Let's take a look at the transform component. The transform component used to contain both the local and global metaphor for a game object. For instanced objects, we no longer want the global transform in there. The global transform now resides in the instance buffer. Now the transform component only contains the local transform plus an index into the instance buffer. In the treewalker function update transform cache, the global transform for each game object is updated if needed and then stored in the instance buffer. This is the function render entities of the render system for PBR. We looked at this code in the last episode. It retrieves a list of entities that have a mesh, a transform, a PBR material, and the instance tag. For each entity, the render system calls update on the instance buffer before it issues the draw call. Here you can see the scene graph in action with access to individual instances. Okay, so this feature is nice to populate your scenes, but it doesn't require especially large quantities of instances. This is different in the grass shader. Since winter is around the corner, I'm showing a variation with ice crystals. It is an example of a shader-only instancing implementation. This is the ice crystal model that we use to populate this rock here. The mesh for this rock is created in the terrain loader from a height map. The grass shader is using a single base transform that we can modify via the scene graph. For each instance, we retrieve a height and a position from a storage buffer. The position is given in the horizontal X and Z plane and corresponds to a pixel of the height map. The height is provided in combination with the position. Let's say the width of the height map is 100 pixels. If the position is provided as 310, the position in the horizontal X and Z plane would be row 3, column 10. Then we can construct a local transform from the position in the X and Z plane and the height in the Y direction and multiply it with the base transform. This is our model matrix. To compute the normal matrix, we need to transpose the inverse of the model matrix, which is this line of code. This example here with the rock and ice crystals uses about 12,000 instances. In this scene, you can also see 4 particle systems for snow, each using 4,000 instances. This brings us to the third application of instancing. I'd like to show today a particle system. For the particle system, we expect higher numbers of instances. We want to support thousands of particles. The particle system has 2 performance optimizations. The first optimization is the particle system does not go through the scene graph. For the snow particle system here, I define a cube in JSON with 2 corners and the pool size. The particle system can then randomly spawn snowflakes within the volume of the cube. Each particle is animated per frame, but there is no gizmo to move the cubic volume around in the scene. Instead, the location is given via a JSON description file. This saves us a mat4 multiplication per particle. In this scene here, with 16,000 particles combined, I saw pretty bad frame times on the CPU side initially. This was the case especially in debug mode with about 40 milliseconds per frame. By removing the particle system from the scene graph, I brought it in debug mode down to 12 milliseconds. Compiled in release mode, it is blazing fast with less than 800 microseconds per frame. The second improvement I made is that I removed the top-level group node when loading the 3D model. The top-level group node is used to retrieve the game object ID for a 3D model or instance from the scene dictionary without knowing its full path. The full path in the scene dictionary is given by a prefix, the 3D model path, the instance number, plus the path inside the 3D file, meaning the name of the scene and the parents and node name. The top-level group node is using the keyword root instead of the path inside the 3D file. By removing the top-level group node, I cut the number of required game objects for the 4 particle systems from 32 to 16,000. The instance tag that instance 0 receives holds a list of all entities. This way, the application can get access to the game object IDs of all particles without calling the expensive dictionary lookup. To wrap this video up, I'd like to show a performance comparison. I'm using this here candle model with 3 different materials for the wax, the flame and the wick. Then I'm using a 16 by 8 by 16 array of candles. That's 2048 candles combined. I'm comparing 3 different setups. Instance draw calls for the 3 submeshes of the candle model, so 3 draw calls. All 2048 candles combined into a single mesh with 3 submeshes for the wax, flame and wick. This also results in 3 draw calls. Individual draw calls for the 3 submeshes of the candle model, so 2048 times 3 draw calls, or 6,144 draw calls in total. I made sure that in all scenarios the camera position and alignment were identical. For performance measurements on the GPU, both the vertex and fragment shader need to be considered. The fragment shader is usually more expensive, so any changes in the order of how the candles are drawn make a difference. If the front rows of the candles are drawn first, these candles occlude the rows in the rear, and a lot of calls to the fragment shader will be culled by the depth test. The other way round, starting from the rear to the front, a lot of overdraw occurs. So when comparing different render techniques, care must be taken to use the same conditions. Anyways, it turned out that the 3 instance draw calls and the 3 draw calls for the single mesh are identical with 2 milliseconds. The 6,144 draw calls for non-instance rendering lead to 11 milliseconds in the 3D render pass. So the instance draw calls are much faster. While they need the same GPU frame time as the combined mesh, a single candle loads faster and needs way less memory. Okay guys, that's it on the topic of instancing. I hope you enjoyed this video. Please like this video and also my engine on GitHub. To watch more videos like this one, please consider subscribing. See you next time. Bye bye.